From the 18th meeting of the Society, we turn to the 2,343rd meeting and tonight's lecture on Hubble, the missions that enabled the Hubble Space Telescope to unravel mysteries of the universe. And it's my pleasure to introduce tonight's speaker, John Grunsfeld. John is Associate Administrator for the Science Mission Directorate at NASA. Previously, he was Deputy Director of the Space Telescope Science Institute in Baltimore and Professor of Physics at Johns Hopkins University. John was an astronaut from 1992 until joining SDSI as Deputy Director. Before becoming an astronaut, he was a Senior Research Fellow at Caltech in Physics, Mathematics, and Astronomy. John made 5 shuttle flights. He visited Hubble 3 times on those missions and performed 8 spacewalks to service and upgrade the observatory. In all, he logged more than 58 days in space and 58 hours and 30 minutes of spacewalk time. His first shuttle flight was in 1995 on Endeavour, his second on Atlantis in 1997. The next 3, including his last, were on Discovery in 1999, Columbia in 2002, and Atlantis in 2009, during which he upgraded and serviced the Hubble, making possible much of what Hubble has achieved for all of us. In addition to these considerable achievements, John has carried out research on high-energy astrophysics, cosmic ray physics, and exoplanets, focusing especially on future astronomical instrumentation. John earned his BS in physics from MIT and his PhD in physics from the University of Chicago. He is the recipient of numerous awards, including the NASA Distinguished Service Medal, the NASA Outstanding Leadership Medal, the NASA Exceptional Service Medal, the National Space Club Engineer Award, the Komarov Diploma, and the Korolev Diploma. Please hold questions to the end and join me in welcoming John to the podium.
Well, thank you very much.
My pleasure. You should be up in a minute, and then I'll be out of your hair.
Well, it really is a pleasure to be here. I spent the last 3 days in Houston in a windowless room with a bunch of other NASA administrators talking about the business of space and exploration. And tonight I'm going to talk about something that I'm very passionate about. And so in spite of missing my plane last night because of the snow here, I could have gotten to Baltimore, but I would have spent the night at the airport and rushing here today. But to talk about Hubble. And to give you a little bit of the punchline, I believe Hubble is the most powerful scientific instrument ever created by humans. And it represents, in our human history, a very unique instrument, observatory, in that it was entirely dependent. Its success has been entirely dependent upon human spaceflight. In part myself and my colleagues being electricians and plumbers and mechanics. When I started studying astrophysics, I had dreams about being a theorist and unraveling the mysteries of the universe, cosmology, and maybe someday winning a Nobel Prize. But early on discovered that experimental physics is actually much more romantic and fun and exciting, and you get to see exotic places. And I think it was that training as an experimental physicist that allowed me to go up to the Hubble and do what I did. As the head of science at NASA, I want to spend just a little bit of time talking about science at NASA, science, the science enterprise. Marcia McNutt, the previous speaker that was discussed a little bit, was also the head of U.S. Geological Survey, also another science agency. That's a picture of me on the last Hubble flight, and it's kind of neat, reflected in my visor is the Earth. This is a picture taken by Drew Feustel, my spacewalking partner, who's an exploration geologist. You can see Hubble in the background. Really a very neat environment. And there's a lot of controversy, and there's been a couple of hearings just recently. Administrator Bolden had a hearing day before yesterday last week, Bill Gerstenmaier, that had a human space flight. One of our other crewmates, Mike Massimino, had a hearing also last week in front of the Senate Authorization Committee with Senator Cruz and Senator Nelson and others, trying to talk about, why do we have a NASA? Why do we have human space flight? Why do we have a science program? What's our mission? And for me, I like to distill things, not necessarily pithy statements, but the kind of thing that's relatively easy to understand. And so when I think about what we do at NASA, we innovate, so we develop technology, we develop ways of doing things that enable us to explore. And when we explore, and it's Earth and space exploration, when we explore, we discover things. It's discovery driven. And this is something that is, I think, programmed into our DNA. And you might say, well, what gene is it programmed into? And I think it's DRD4, and for some people an R7 variant, that it compels us to explore. And when we discover things, we feel rewarded. And of course, it's something that humans do very well. And also when we discover things, it allows us to inspire others. This is a picture of the first dwarf planet that humans, as far as we know, have ever entered orbit around. This is Ceres, and today, the Dawn spacecraft, after a 7-year voyage, entered orbit around Dawn. Now, Dawn in the Hubble Space Telescope is sort of a blurry, round, planet-looking object. It's a dwarf planet by the current definition. And it could have been the Death Star from Star Wars, but it turns out it's not. But it is really interesting. It's about half the diameter of Pluto. And already we're seeing some interesting things where there's this bright spot. And the bright spot has a partner. And we have no idea what it is. But tonight we entered orbit. It's going to take us a few months to do the imagery, but we're going to spend the next few months studying Ceres in great detail. So that's a very exciting thing. If you want to find more about it, go to dawn.jpl.nasa.gov. So that's the big excitement today. Why do we study Earth and space science? Well, it's a good job if you can get it. I suppose that's one reason. And it is very exciting. But at its essence, we're trying to answer some fundamental questions. Some of them are very practical questions. What causes the weather, earthquakes, climate change? What causes the sun to vary? Of course, all terrestrial weather essentially is caused by the rotation of the Earth and solar heating of the Earth. And a few other details, a little bit of chemistry, a little bit of topography. How does the sun affect the Earth? Where did the universe come from? How did it form? How did it get to be the way it is? How did the chemical elements that we're made out of form from hydrogen, helium, and a tiny bit of lithium out after the Big Bang? And if we didn't have all these heavy elements like carbon, iron in our blood, calcium in our bones, just a universe with hydrogen and helium, then we'd all talk like this. And life would be very uninteresting. Actually, there'd be no life at all. And then the big question, we are here, and the Kepler telescope, the NASA Kepler telescope, has been staring at a region of space in the constellation Cygnus for almost 4 years, and it's discovered thousands of other planets. Based on the statistics, the inference is that every star you see in the night sky has a solar system around it, with multiple planets. And a good fraction, maybe a fifth of those, have a rocky planet somewhere near the size of the Earth. And a good fraction of those are in a region away from its star where liquid water could exist on its surface. Roughly speaking, don't go and write scientific papers on this because you'll get rejected. But there's about 40 billion Earths in our galaxy. 40 billion. Now, we haven't seen any of those yet. Future telescopes are going to hopefully discover those, and I'll talk about that. But if there's so many planets that are just like Earth, that have been like that for billions of years, scientifically we can now ask the question, are we alone? Is there an Earth 2.0 with life on it? Is there intelligent life on it? Is there intelligent life on Earth? But that's another talk. I like to frame what we do in NASA science, not whether it's Earth science, planetary science, heliophysics, the study of the sun and the connection to the Earth, or astrophysics, but in a kind of connection diagram. because all of our science is interconnected. I've talked about the origins of the universe, and we're trying to study how did the universe evolve after the Big Bang? How did galaxies form? How did the first stars form? Did black holes come first, or did galaxies come first? What was the cycle of the early stars that converted hydrogen and helium into those heavy elements? When stars started forming, did planets start forming at the same time? Do planets form when a star forms, or is that a later activity? And then how do those stars and solar systems evolve? How do planets evolve? And studying even on Earth, the geophysics, the geology of once life turned on, how did that change the essential geology and the atmospherics and the climate on planet Earth? At the same time, we're studying the field of astrobiology, which is really the question of, what kind of life could there be on Mars? Could have been on Mars if it's not there now. Europa, a moon around Jupiter, Enceladus, a moon around Saturn. One of these exoplanets, what's the range of life? And one of the ways we do that is by studying extreme life on Earth, life in deserts, life near volcanoes, life deep under the sea. It's the field of astrobiology. And trying to see if we can learn something about studying current life that might inform us about how life started on Earth. And then how did that life change the evolution of the Earth? And it did quite markedly. And how are we changing the evolution of the Earth's atmosphere and the oceans and the chemistry on Earth? And all of that involves an enormous amount of fundamental physics and chemistry, interstellar chemistry, photochemistry, ultraviolet light ionizing molecules, creating new molecules. We see all the essential building blocks of life in molecular clouds. Alcohols, caffeine, sugar, all of those things are in molecular clouds. And there's all kinds of feedback mechanisms, and in the end, a lot of technology that's common between these two studies. And in the end, there's two very important questions. One which drives me, are we alone in the universe? And another one, really, is human life sustainable on Earth? We know that cockroaches will survive almost anything. Unfortunately, of these two questions, this one is actually a known. Life is not sustainable on Earth with great certainty for two reasons, one of which our sun evolves. Our sun is about 5 billion years old. A sun like ours has a life of, roughly speaking, about 10 billion years. And in the next 5 billion years, the sun is going to continue to burn its hydrogen in the core, run out of fuel. It's going to start swelling up, become a red giant. The Earth will actually be in the sun's atmosphere, and all life on Earth will be gone. So lest you run out of the room screaming, we don't have to worry about that for a few billion years. And given that modern humans have only been around for some tens of thousands, 100,000 years, in the billion-year time frame, that's not something we should worry about. If you want to worry about something, you could worry about the fact that the Andromeda Galaxy is on a direct collision course, our nearest neighbor, with the Milky Way. Fortunately, the distance between stars are so great that there are very few star-star collisions, almost none. A lot of gravitational interactions. The Earth might get ripped out of the solar system and be sent off some trajectory to float freely in an icy tomb through interstellar space. Pretty unlikely. We have about 3 billion years before we need to start worrying about that. So I'm not going to stay awake at night worrying about that. We could get hit by a big asteroid. 65 million years ago, the Earth was hit by a big asteroid. But that's not going to wipe out all life on Earth. In fact, we are here in large part because the Earth got hit by a large asteroid, wiping out most of the dinosaurs, created an environmental niche for warm-blooded marsupials, from which then the rest of the mammals evolved, if you believe in that kind of thing. And we're here to have a Philosophical Society of Washington discussion about evolution, about the origins of life, the origins of the universe, but more practical matter. What are we doing today, human influence and natural influences, that will determine what our lives will be like in 10 or 15 or 50 years, our children's lives over the next 50, 100 years, grandchildren? We are on a profound trajectory that has two characteristics, one of which is we know we are markedly changing the Earth's atmosphere and oceans. that we are driving that through human activity, and there's really, there's no doubt about that in most circles outside of this town, and that we have the sentient ability to ask the question and understand the science. I mean, these two things together are what give me great hope. Now, what's the story so far? I've told you science is trying to unravel this story of the history of the universe, so let's start at the beginning. So this is my last slide. It's going to take me 1 billion years to go through. But it starts with some moment in time, 13.72 billion years ago, and something happened, and I can't tell you what it is, and science probably can't tell you what it is, but the universe was created. There was a period of remarkable expansion. This is the so-called inflationary universe. And the universe grew in size by many, many orders of magnitude, expanded, the chemical elements condensed out of the early soup of exotic particles, and it cooled enough that for the first time, about 372,000 years after the Big Bang, that light could travel freely throughout the universe without hitting something. That's the first thing we can see, and that's the cosmic background radiation. And fortunately, many of you are old enough in this audience, like me, to remember that with analog televisions, you could tune channels, and as you were going between channels, there was the fuzz in the light. Well, televisions or microwave receivers, you were actually seeing part of the cosmic background radiation on your television. It pervades everything, the whole universe. And the Cosmic Background Explorer imaged that ancient universe and saw that we evolved from this universe just according to this timeline in the story, and we were able to start understanding the fluctuations in that background radiation that now accounts for the whole cosmic structure that we see of galaxies and dark matter and dark energy, but I'm getting ahead of myself. Sometime around 400 million years after that, the universe was cooling, gravitation was pulling matter together. I described that there was hydrogen and helium, trace amounts of other elements, principally lithium. And as the matter started to collapse, it started heating up, just adiabatic heating. And at some point, stars were born, the very first stars. Now, we haven't seen this, but we're building a telescope that will, and I'll talk about that at the end. But we know that this happened because we see galaxies in the universe today, because we have a sun. We have a sun that we live around. It's easier to talk in the daytime. I can point right where it is, but I think it's right about there. And with the Hubble Space Telescope now, we've been able to observe from where we live in our suburban galaxy all the way back to within the very first galaxies. We're seeing toddler galaxies, not baby galaxies, but toddler galaxies, as they were around 500 million years old. So there's this window between essentially, the first few 100,000 years and when the first stars turned on that we have not glimpsed yet. But the whole rest of the universe, galaxies forming, galaxies colliding, galaxies getting disrupted, supernovas going off, we've been able to map and record the history of 13 billion years of the universe, including close to home, where, of course, we've observed the Earth, and we've observed planets nearby in our own solar system, planets in other solar systems, and put together a story that's pretty phenomenal, that tells the whole history of the universe. Riccardo Giacconi, who's one of the fathers of the Hubble Space Telescope and the Space Telescope Science Institute, captured this somewhat eloquently when he said 21st century astronomers should be uniquely positioned, and we are uniquely positioned, to study the evolution of the universe, to causally relate the chemical elements that were born in the Big Bang and those first moments, and even inflation, all the way to the formation of life on Earth through RNA and DNA. And we're making great progress in this vision. Now, one of the folks who helped that vision was a University of Chicago astronomer, Edwin Hubble. What's not well known about Edwin Hubble is that he was a high school track star. He set the Illinois high jump record in high school. This would have been around 1905. And At that time, the record was about 6 feet 3 inches. This is before the flip. But he was interested in science. He got a law degree. How many attorneys are in the audience? Yeah, quite a few. So he got a law degree because his father insisted he did, but he didn't really like that very much, so he went back and got a PhD in physics from the University of Chicago in astronomy, and went on to be one of the preeminent American astronomers, and actually spent a lot of time looking at fuzzy objects. Now, this was after he was on the University of Chicago basketball team, which you all know the history. We just are in basketball college championship season. I'm sure you know that the Maroons were national champions 1908, 1909, and 1909, 1910. I didn't see their name in the listing this year. I'm not sure what's up with that, but anyway, he was a power forward on the basketball team at the University of Chicago, the Maroons. But he spent a lot of time looking at pictures like this. Now, at the time, we didn't know what this was. Some of you, because you're either professional or amateur astronomers, know that M31 is a galaxy. But what he saw was just a fuzzy blob. And astronomers called these nebulae. And nebula, gaseous. They thought they might be balls of gas. And they knew that there were stars, that we were looking at. But what these were, was somewhat inconceivable, because at the time, the view was the universe is just an infinite collection of stars that go on forever. Now, this is actually photographic emulsion that was laid down on a piece of glass that Hubble would put in the telescope, and then he would look through an eyepiece and guide the telescope on one of these target stars for hours at a time, and then he would give the piece of glass to a technician. They would develop it like a dark room, and this is what you would see. It doesn't look very familiar to us because it's a negative. Now, fortunately, we have Photoshop, so I can invert it. So now it looks a little more familiar. So these are stars, and this is this gaseous object. Well, what he discovered is a bright object in here on the 6th of October, 1923. And this object was pulsing. And he and others recognized that this was a particular type of star called a Cepheid variable. And this star, roughly speaking, has an intrinsic luminosity. So what's luminosity? Luminosity is like, if I say a 100-watt light bulb, while we still have incandescent light bulbs, a 100-watt light bulb produces a certain amount of light, and you know how bright it is if it's 1 meter away from you, and you know if you put it 3 meters away, because of the 1 over r squared law, that it will be 1/9 as bright. So if you see it and it's 1/36 as bright, you know that it's 6 meters away. So it gives you a way to determine a distance scale. So he recognized that these variable stars in this gaseous object were these Cepheid variables where other astronomers had calibrated the distance, and he measured the distance to M31, and it was phenomenally distant. And so he undertook a program of looking at these variable stars in other fuzzy objects and determined, in fact, that they were so far away that, and he and others determined that these must be massive collections of stars that were coined island universes. Now, island universe is not a very catchy term. Someone else said, how about galaxy? And it stuck. This is a galaxy. This galaxy contains about 400 billion stars and is much like our own Milky Way. This is the one that's going to collide with us, but you don't have to duck anytime soon. Well, by measuring this distance scale and using spectroscopy, he was also able to measure the velocity of these galaxies. And on average, he saw that all the galaxies were moving away from us. Now, this provides a real conundrum, because either we're in the center of the universe and all the galaxies are moving away from us, or the universe is expanding and every galaxy would see all the other galaxies moving away from them. Now, if we were in, the 1600s, of course, the conclusion would be that we're at the center of the universe because we're very special. But Einstein was around now, and others, and this was the discovery that the universe was expanding, and by inference, at some time previously, it must have all been tiny space and the origin of the Big Bang theory. So Hubble was the discoverer of that. So as a result, we named the Hubble Space Telescope after Edwin Hubble because of his prowess in basketball, and a little bit because of astronomy. And this is the Hubble as we all know and love it. It's about the size of a big bus, a tour bus. Not a particularly large mirror, 2.4 meters across, 94.5 inches. But because of its unique location orbiting the Earth, it's above the atmosphere, so stars don't twinkle. You don't have the aberration of the light going through the atmosphere. And not all light goes through the atmosphere. I'll show that in the next slide. And it's very steady. So if you look carefully at the screen, you'll notice that the Hubble is shaking. I don't know if this will work, but maybe. Anyway, if we all get up and jump, I bet we can make that shake some more. Well, astronomical observatories on Earth all shake as well because of earthquakes across the globe, because of a truck driving by, because of wind on the observatory dome. Hubble doesn't have any of that, so it can point very steadily. So the fact that it's above the atmosphere, can point steady, and can get light that doesn't even make it down to the Earth is a unique position that's allowed Hubble to make many of these discoveries. Now, Hubble sees very much in the same visible light that we see. We think of the colors of the rainbow. That's what we can see with our human eyeball. Hubble can see a little further. It can see some ultraviolet light, all the colors of the rainbow, and a little bit of infrared light. Now, if you kind of blow that up, this is what Hubble can see. So this is the light we see, typically. You can see a little bit more ultraviolet all the way to the infrared. And that extra light that it can see is very important. If we really want to understand all of astronomy, we want to see stars and planets and galaxies as they emit in radio waves, in ultraviolet light, in X-rays, the full electromagnetic spectrum, because each part contributes a little bit different physics. Because of the expansion of the universe as well, light that was emitted as ultraviolet light by early stars stretches with the universe too and becomes infrared light. So if we want to look at the early universe, we want to look in this infrared light. If we want to look at things that are very hot or very energetic, like the aurora on Jupiter, we want to look in ultraviolet light and everything in between. And this shows some of the different instruments, but I'll talk more about that. Now, astronomy is an itch that's been, I think, with humans ever since we started becoming sentient and looking up at the heavens and asking, what's out there. There were a few cultural biases against trying to interpret the never-changing perfect heavens, at least in Western civilization. This is a page out of Sidereus Nuncius from Galileo. And one of the things he observed is Jupiter and some bright objects around Jupiter, and he noticed that they changed their locations over time. And he discovered the Galilean moons, and he thought, isn't it remarkable? They're named after me. Anyway, he discovered moons around Jupiter. The four brightest we have named the Galilean moons, and we continue to observe them, and they behaved in the same way, as far as dynamically, as the planets around the sun if you use a sun-centric model. Well, how did he do that? He used a telescope. He used a telescope much like this. It was about 1 meter long. It had tiny little glass lenses. It was covered in leather from cows on a certain herd in Italy. It was made from wood from a certain tree in a forest near his house. Now, he didn't invent the telescope. He made the telescope better. But he was one of the first ones to use it rather than for national reconnaissance to look up at the sky. I mean, people typically use the telescopes to spy on their neighbors or to spy on ships, or things like that to see, at great distances. And he pointed it at the sky, and we carried a replica of his telescope made with the same leather from the same herd of cows, apparently. That's what we were told. Now, different cows, but, the descendants. Wood from trees that were descendants of the same trees, and by craftsmen in the same glass factory from the same sand. And I can tell you one thing I know about Galileo. He was a very patient observer, because this was a really rotten telescope. It was very hard to use. You had to be incredibly patient. It was only clear right in the middle of the field of view, unlike modern amateur telescopes, that are practically Hubble Space telescopes themselves. and auto point and all that kind of stuff. But this was very hard to use. And I used it to observe Jupiter. And you could marginally see those moons. And I was in space when I did that. This is on the aft flight deck of the space shuttle. So if we consider the power of the human eyeball as one unit of light collection, the amazing thing Galileo did was to develop a telescope that had 100 times the light gathering capability of the human eyeball. And it was that increase in light collection and resolution that allowed him to make a number of discoveries in astronomy. And kicking off a scientific renaissance in the process. Well, telescopes continued to get bigger, and people developed better optics and eyepieces. And then there was sort of a privately funded battle for who could build the biggest telescope. And that lasted for a while, and a lot of scientific discoveries were made, getting up to 4-foot telescopes. Eventually, it became more of a scientific enterprise, especially when reflecting telescopes were invented, where you could make much larger optics than making lenses, which are refractory telescopes, resulting in the Mount Wilson 100-inch telescope that Edwin Hubble used to make his discoveries. Actually, it was the Hooker telescope on Mount Wilson, and then the 100-inch reflector later. And an amazing thing happened mid-century, last century. Photographic film was replaced by electronic detectors. And this gave us another order of magnitude sensitivity, ability to collect light. And suddenly, the sensitivity and the discoveries we started making went way up. We went to the 200-inch Palomar telescope in the 1950s, a huge piece of glass, very thick, but an amazing amount of light collection. The Russians, the Soviets built a 6-meter. It never really quite came up to the potential of the Palomar because the Palomar had just such a perfect surface. Then electronic detectors so prior to that, people were just using eyeballs and sketches. Then we had that photographic emulsion, and then the electronic detectors. This is what Hubble did for us. The Hubble Space Telescope, gave us orders of magnitude of factors of 10, factors of 1,000 over the best telescope at the time. 10 billion times better than the human eyeball, and 100 million times better than Galileo's telescope. But there's more. Because the Hubble Space Telescope was serviceable, we could bring up new instruments, new technology. Hubble was launched in 1990. How many of you remember what kind of digital camera you could buy in 1990? Basically none. When the Hubble was built, the first CCDs had been invented, and Hubble flew one, and they were extremely expensive and experimental. That's not that long ago. Imagine how far we've come. So with the newest cameras that we just installed, we've been able to go off the scale with the ability to be more sensitive and have a better resolving power and take advantage of Hubble on orbit. Now, many of you remember, if not all of you, how many of you were born after 1990? I know there's at least one person in the audience, so a few. Okay, so you don't remember this. But when Hubble was launched, it got to space. It was called the first of the great observatories. And the first images came down, and people said, it's pretty good. I wouldn't call it great, but it's pretty good. There was something wrong with it. And the mirror had been ground absolutely perfectly to within 1,000th of the width of a human hair perfection. Except for one thing. It was the wrong shape. And it's a long story. I won't tell it tonight. You can ask a question about it later if you want. But it was pretty easy to detect looking at the images that the mirror had something called spherical aberration. And again, at the edge, if I remember correctly, most of the mirror was close, but by the time you got to the edge of this 94.5-inch mirror, the difference between the shape we wanted and the shape we got was about 1/40th the width of a human hair. And that was enough to go from great to good. You've heard of the book, Good to Great? This was from great to good. And it wasn't a good thing at all. In fact, it was a disaster for NASA because this was, in those year dollars, about a $2 billion observatory. It promised to unravel the mysteries of the universe, and it wasn't going to. but it also signaled that NASA couldn't build big projects anymore. We'd done Apollo, we built the space shuttle, we wanted to build a space station, but if we couldn't get a telescope right, how could we possibly build a space station? And so this was a comic that sort of captured the time. This is what the moon looked like, Jupiter, Saturn, and angry taxpayers, and an angry Congress. So how did we fix it? Well, once we knew what the wrong shape was, it was pretty easy to imagine that you could put contact lenses on the observatory. Now, technically a little more difficult than just adding contact lenses, but we knew if we could go up to the Hubble and put in the optical train some kind of mirror or lenses that had the inverse shape of the wrong shape, that would correct it. And so we built two new instruments, one called the Corrective Optics Space Telescope Axial Replacement, or COSTAR, NASA loves acronyms, and then a new wide-field digital camera that would have these corrective optics in it. But we had to put them in the telescope. So Hubble was launched in 1990. Our current NASA administrator was the pilot on the mission. Now you may think the pilot is the guy who flies the space shuttle. That's actually the commander. So you can imagine two pilots on a space shuttle. One's called the pilot, one's called the co-pilot. What does the co-pilot feel like, right? Second-class citizen. So they name the pilot the commander and the co-pilot the pilot, and everybody's happy. But we're really lucky. Charlie Bolden's a great guy, and he helped launch and deploy the Hubble Space Telescope. And in 1993, we sent up a crew to try and save NASA and fix the Hubble Space Telescope. And fix it they did. NASA's communications and public affairs folks could not have come up with a story as compelling as the real world. Nobody, of course, would have put a flaw in the telescope to boost NASA's fortunes. But NASA did ride on the edge of having any relevance, being able to continue to fly the shuttle or have a space station. And so women and men in white suits, the spacesuits, rode to the rescue like an old Western and saved the Hubble Space Telescope there's a typo, the Wild Field. I like that even better. The Wide Field Planetary Camera and the COSTAR put in some new gyros, put on new solar arrays, and after that, it was phenomenal. The telescope actually did become a great telescope. It measured the age of the universe. It verified the existence of black holes. It watched an impact of a huge asteroid on Jupiter. It saw the beginnings of stars, where stars are born, where stars die. Really met all of the objectives of the Hubble Space Telescope as it was imagined. Then in 1997, the second servicing mission, again, men and women actually that was an all-male mission, men going up to service the Hubble Space Telescope, putting in new cameras, fixing a few things that were going wrong. And then in 1999, my first Hubble mission, this was my third space flight, we were getting all ready to go, and we were going to do 6 spacewalks and do a complete renovation of the Hubble to bring it up into modern times. And a bunch of the gyroscopes that allow Hubble to point very steadily, unlike the projector, failed, and Hubble went dark. And so over Christmas of 1999, we had to do an emergency mission to go up and save the Hubble again. So we put in the new gyros, a new computer, a few other things, a fine guidance sensor, and got Hubble back working. And then we came back in 2002 to finish off the job, putting in a new super-duper digital camera, a 16-megapixel camera. If I had briefed this right after the mission in 2002, if I had said 16 megapixel, people would have gone, ooh. Now you can get one at Walmart. But at the time, it was pretty good. It's still an amazing camera. New solar arrays. Hubble had another problem with the power control. Basically, its main fuse box had a problem, and people thought the Hubble was only going to last a couple more years. And so I replaced that. And then I replumbed the telescope with a new cooling system. And everything was great because we had one more servicing mission on the books, servicing mission 4. It was going to fly in 2004 to put in a new spectrograph that breaks light into its component colors to study all kinds of things, hot stars and galaxies. A brand new wide field camera with the newest super duper detectors, put in a new fine guidance system, a cooling system, batteries and gyros and all of that. But in 2003, we lost Columbia. And the NASA administrator at the time, Sean O'Keefe, I was the NASA chief scientist, said, no-bore Hubble missions, too risky. And all of this was basically off the books. And at that time then, Hubble would have only lasted until about 2009, was the thought. And the batteries would die, and Hubble would start slowly spiraling into the atmosphere, as it's still doing now, but that we would have lost the Hubble. Fortunately for us, for Hubble, a subsequent NASA administrator, Mike Griffin, asked me if I could put together a team of folks to study whether we could go to Hubble in a way that would minimize some of those risks. And so we put a plan together, and he accepted it. And in 2006, on Halloween, he announced that we were going back to Hubble, and he asked me to go on my third Hubble mission. And so in 2009, we actually flew that mission. So here's the crew that we put together. I brought back Scott Altman. He had flown on the 2002 mission. He's an aerospace engineer from the University of Illinois and a test pilot, flew F-14s in the Navy, captain in the Navy. So this was his fourth mission, his second to Hubble. I brought back Mike Massimino. He was the astronaut who just testified last week. He's now a professor of mechanical engineering at Columbia. He's a mechanical engineer. He had been on the 2002 mission, so I wanted some experience. So he led one of the spacewalking teams. Of course, myself, this was my fifth mission, my third Hubble mission. I was the Hubble lead. My spacewalking partner, Drew Feustel, his first mission, he's an exploration geologist and works on cars, old cars. He works on BMWs, and he had some kind of weird Dodge that he had rebuilt, but he sold that. It wasn't a Dodge Dart, but I like to say Dodge Dart because I'm a big Car Talk fan. Megan MacArthur, our flight engineer and robotic arm operator on her first flight. She's a physical oceanographer. Greg Johnson, another Navy pilot. He flew A-6 attack aircraft, ground attack, and had worked a lot with high-altitude aircraft. This was his first flight. And Mike Good, an Air Force aerospace engineer, on his first flight. So we had a fair number of new flyers, and this was a bit of a challenge, but all very talented folks. And one of the ways that we were able to say we could go back and perhaps avoid some of the problems of Columbia. First of all, for those of you who don't know, we lost Space Shuttle Columbia because on ascent, a piece of foam from the external tank, the big orange tank, fell off, hit the leading edge of the wing, broke a hole in the very delicate carbon composite, and it wasn't discovered. So when it came in to land after a 17-day mission, the hot gas, several thousand degrees Fahrenheit, entered the wing, burned off the wing, and the crew perished over East Texas. So the question is, if we launched and a piece of foam hit our wing, what would we do? Well, we wouldn't want to come back in the atmosphere. We can't go to space station. Hubble's in a completely different orbit. Any of you seen the movie Gravity? Not possible. So what I came up with is a very inexpensive, clever solution. Put another space shuttle on the other launch pad, and so if we got in trouble, the other shuttle could come up and rescue us, and we worked out all the shuttle techniques. Now that's a very expensive thing to do. And it costs several $100 million to prepare a space shuttle and train a crew to be ready to go on short notice to come up and rescue us. But Hubble was that important to NASA, to the administrator, and to the country that we were willing to do that. So finally, in May of 2009, here we are on the launch pad. That's Endeavour, our rescue vehicle. This is Atlantis, which means when you go out to the launch pad on launch day, you got to make sure you turn right, not left.
All right, let's go!
We're in our orange suits. These are launch and entry suits. We call them pumpkin suits. They're to make us feel better. I mean, if you jump out of a shuttle, those don't help you, but we wear them. This is launch day. You can see there's oxygen boiling off, liquid oxygen, nitrogen. It's a pretty tight fit in the shuttle. Wear parachutes, again, to make us feel better.
Go, got it, go. Payloads, go.
It's a great day to go fly. So on behalf of the KSC Processing and Launch Team, I'd like to wish you, your crew, and the whole Hubble Space Telescope team a great mission. Good luck, Godspeed, and we'll see you back here in about 11 days.
So we're relying on about 10,000 people all to do their job just right, many of whom are the lowest bidders. And about 6 seconds before launch, we start the main engines. Once they're all checked out, we fire the solid rocket motors. As soon as we light those solid rocket motors, we're going somewhere. And that noise you hear is a master alarm. That's a bad thing. I'll tell you about that once we get to orbit. This is a camera looking down from the solid rocket motors. Here we are zooming up, going well faster than the speed of sound. You can see our trail. At 2 minutes, we get rid of those solid rocket motors. So these are the cameras on the solid rocket motors looking up. And these solid rocket motors go all the way into the ocean. And you can see, there we are, still speeding away for another 6.5 minutes. And then we get rid of the external tank. You can see how burned it is there. That'll burn up over the Indian Ocean. Most of it will burn up. And then, so 8.5 minutes later, we're doing 17,500 miles an hour, orbiting the Earth. We open the payload bay doors. These are radiators. They have Freon in them to help get rid of the heat from the orbiter, and we're on orbit. Now, I'm a Hubble hugger, and I had spent, a lot of my life and risked my life to go up to Hubble, and then Hubble was canceled, and then I was able to get it back, and then we trained a crew, got on the launch pad, got down to the launch time. We were going to go in October of 2008, but a hurricane hit Houston. Megan MacArthur lost her house. It was flooded. We all had to evacuate Houston, and we finally got to the launch pad, and we had liftoff and that master alarm. And it was a bad alarm. It was a flight control system. Now you may say, well, what's a flight control system? The flight control system is the ensemble of computers and electronics that sends the signals to move the engines so that the craft knows where to fly. Not only the main engines, the liquid engines, but the solid rocket motors, and also the surfaces, the elevators, on the space shuttle's wings. Because as the shuttle is taking off through the lower atmosphere, those wings are generating lift. And so we actually use the elevators to spoil that lift and make it not lift. So the wings don't break off, which is generally a good thing. So right at liftoff, we got an annunciation that one of our flight control systems had failed. I mean, what are the chances it would happen right at liftoff? Why not a minute before or a minute after? Well, it turns out the engineers who built the space shuttle were really brilliant. I mean, truly brilliant. And they thought of almost everything. And they realized that once they started those main engines, or even very close to flight, within the last 30 seconds, but in this case, within the last 10 seconds, that if they enunciate a really bad alarm, there's no situation that a crew member can't make worse by a wrong switch throw. We're human beings. In the heat of the moment, a crew member might flip a switch, turning something else critical off, and the space shuttle would launch and blow up or launch and veer off course. So in the software for the shuttle, they said, within the last few seconds, no matter what happens, don't sound the alarm. Because we don't want to scare the crew into doing something rash. Now, if it's more than 10 or 15 seconds out, we'd be able to talk to the folks on the ground, talk to our other crew members, and say, yes, we're going to turn that switch. That switch will tell the computer to shut down the main engines and we won't go anywhere. What they were worried about is, in the last few seconds, we'd reach up, flip off the switch. It would be within 2 seconds of those solid rocket motors going off. The computer would see the switch, the computer switch going off, and say, okay, kill the main engines, but the solids would go anyway. I told you those solids are pretty powerful, 3 million pounds of thrust. So the solid rocket motors, if they light, will lift off. But without the main engines, they're going to lift off without the shuttle. And now you have this huge external tank filled with liquid hydrogen and liquid oxygen. The main engines aren't running, the shuttle would go down. There'd be a big explosion, and there'd be a lot of explaining to do. Just not us. So the engineers said, no master alarms. Okay. So somebody said, well, when should we tell the crew? Somebody said, how about at liftoff? That's what they did. Now, we didn't know that. They could have waited a few seconds. It would have been a kind thing to do. But in my mind, I was thinking not, okay, no big deal, or, oh, big deal. I was thinking, damn, we're not going to get to Hubble now. Fortunately, they were so smart, they put in 4 flight control systems. They're so critical that they said, we better put a bunch of them in there. And they vote. Okay? And if they disagree, so if there's 4 flight control systems and 1 disagrees, so 3 of them say, turn the engines right a little bit, one of them says, turn the engine left a little bit, they decided they're going to vote out the one that's different. Okay? So they're culturally insensitive, but technically it makes a lot of sense. And so they would declare that one failed, and then you have 3 good ones. Okay, what if another one fails? Well, now 2v1, okay, you fail another one. Now you're in a situation with 2, you can't tell the difference. Then they just say, disagree, you figure it out, meaning us. But that gives us at least fail safe, and then some redundancy. So we could actually go down to 1 if we guessed right. We never got there. Fortunately, the alarm was that some solder ball or some wire had shorted out and killed one of the flight control systems. So there was nothing to do, and we just continued to orbit. Now, 30 seconds later, we got another alarm that said we were going to have to do a very risky return to launch site maneuver. Then I was convinced we weren't going to get to Hubble. But fortunately, the ground capsule communicator, another astronaut, said, you're pressed to orbit. And that surprised us all, but still a good thing. And he could have said, press to orbit, sensor only. It turned out it was just a bad transducer, a bad sensor. But we made it to orbit. We got to work to change the space shuttle, Atlantis, from a spaceship, a rocket ship, into our home in space. We started chasing the Hubble Space Telescope. This is Scott Altman, our commander, wearing a really cool astronomy cap. We had caps made with the Hubble Deep Field on them. And all the other astronauts made a lot of fun of us, but that's okay. That's actually a galaxy. It's not like some food that got stuck on there. But he actually is flying the space shuttle up under the Hubble. This is on our 3rd day. And Megan MacArthur is our robotic arm operator, and she's going to reach out and grab the Hubble. Now, this was her first flight. It's her 3rd day on orbit. And, she looks calm, cool, and collective. You can actually see in the television monitors, the Hubble, images of the Hubble, a little out of focus. And the arm is, just a mechanical extension of her. She has a controller that controls the joints pitch, and one that can translate in and out. Very primitive robot. And she's never actually flown it before. Because on the ground, we don't have an arm that can sit there in 1G, in the force of gravity. So we do it all with computers these days, computer simulators. So effectively, she's done all her training on a computer game, and now she's going to go and grab the most significant scientific instrument ever created by humans, worth in 2009 dollars, somewhere around $8 billion, and beloved by scientists around the world. You think she's under any pressure? Anyway, she did a great job. She got Hubble the first time, which is good, because if she'd bumped it or missed, Hubble didn't have enough power to make it around the Earth again. We're going around the Earth once every 92 minutes. And so she reached out and grabbed someone, Edwin Hubble, the telescope, or Hubble, the telescope, special grapple fixture, looking out over the overhead window. Now, just after that, next day, we got into our spacewalking pajamas. This is Mike Massimino, Drew Feustel. Everything we do has a procedure associated with it. So Mike Massimino has the how to get dressed for spacewalking procedure. And you can see that it's a little bit crowded. Now, this is equivalent to being in recreational vehicle sized for maybe 4 people, minivan type, with 7 people in it, 4 spacesuits. Okay, so now we're up to 11 people, and all the gear we would need in case we had to try and repair the shuttle ourselves. That's what's in these big bags. And food to stay on orbit for at least 25 days in case we have to be rescued. And all the gear we need for spacewalking and spare parts and tools, 460 unique tools for Hubble. So it was a little bit crowded, and that's why you see it there, a little bit crowded. And that's why I like to go outside for a walk. Get some fresh air, get away from all the cramped spaces. So we got into our spacesuits. Here's Drew, here's myself, that's Scott Altman, commander. You can see we have all our tools ready on our tool belts. Everything has to be tethered because we're floating. Everything's in free fall. So if you let go of something, it'll float away. So we have little spring-mounted tethers. And you'll see some of that later on. This is the hatch. If you turn that handle, it lets the air out of the airlock, and we're in a vacuum. And people have told me for most of my adult life, and probably my young life too, that what, do you work in a vacuum? And I get to say yes, I do. But Scott Altman's not supposed to be in a vacuum. He's the shuttle commander. He has to fly the mission at the end. And we were always telling him how great the view is, just one piece of plexiglass between us and the universe. And he wanted to see that too, but we highly encouraged him to get out of the airlock, which he did.
Okay, John, you can open the thermal cover.
And out we go.
Tapped.
So I'm opening the cover to go outside.
Thermal cover is open, Mass. That's great, John. We see you coming out. You can egress. Coming out. Ready, Drew? I'm ready, John. Let's go do this.
So you can hear I'm pretty pumped up at this point, pretty excited. And I love spacewalking. Here's a picture of me as I came out of the airlock. Hopefully you can see big grin on my face. There's the Earth reflected in my visor. My spacesuit, my backpack. The backpack has oxygen, batteries, has a lithium hydroxide canister. That's a chemical that takes carbon dioxide out of the air loop. It's actually an oxygen loop. Now this is a spacesuit that's pressurized to 4.3 pounds per square inch, so about 1/3 of an atmosphere of pure oxygen. Because it's a low pressure, it has to be pure oxygen, otherwise we'd get the bends, so we get rid of all the nitrogen. But it's still kind of like a balloon. It's pumped up, and so you have to fight the suit to move around. Fortunately, you've spent a lot of time in the spacesuit. We have really good stuff. Here's all the tools. They're all tethered. And I'm so excited because this is the first day. The Hubble Space Telescope's in the back. Here's that delicate front edge of the wing, the shuttle wing, and the blackness of space. It's really black because in the daytime with the shuttle, the cameras are going to have to be stopped down so that this is correctly exposed. So you don't see any stars at all during the daytime. And you don't have the atmosphere to fuzz the light to make it blue. So that's why space looks really black. But I look really happy because this is what I live for. This is what I feel like I was born for. And the first day is the easiest day on the whole mission. So I'm looking forward to going out and doing a good spacewalk and upgrading the Hubble with this super-duper digital camera that's going to unravel the mysteries of the universe. So Drew and I got out there. So this is me. You can get a sense for how big the Hubble is. Now, this is correctly exposed. The Earth is so bright it's overexposed. I'll show you some pictures of the Earth later. Solar panel on the Hubble. These are the star trackers. This is the robotic arm. And Drew Feustel is now riding in ski bindings on the end of the robotic arm. And he's playing with a wrench. And this is the old wide field camera 2. We're going to take the wide field camera 3 out of this and put it in once we take the old one out. And right away we encountered a problem. The reason this was the easiest task on the whole mission is there were just 2 bolts. And they're pretty big bolts. One of them disconnected the connector, electrical connector, and one of them actually disconnected the instrument from Hubble. So really one bolt, you unscrew it a bunch of times, and you pull the old camera out, put it aside, you grab the new camera, you put it in, and drive a bolt. When Drew went to drive the bolt, he couldn't get it to turn. It was stuck. And this was really bad. We came all this way to put in the new camera, and we couldn't get the old one out.
I guess before we break the A-latch, which is a game-ending activity, so we ought to try that short adjustable. Okay, here we go.
Here we are, trying one last-ditch effort.
I think I got it. It turned. It definitely turned. Yep, it turned.
I told you how brilliant the shuttle designers are. The Hubble designers are way more brilliant. They anticipated almost everything. This camera goes into a huge hole on the side of the telescope. You may see it in a picture or two. If we broke off the bolt, where does a bolt break usually? Now, if there are any mechanical engineers, you know that if you have a bolt head and a shaft and a bunch of threads, it usually breaks right at the threads. So then we'd take out the camera, but the threads would be stuck in the telescope, and we wouldn't be able to get the new camera in, and the old camera wouldn't stay in, and we'd have a big hole in the side of the telescope. And experts generally say the light should go in the end of the telescope, not in the side. Plus, it's a heat leak. We'd basically, if we broke that bolt, would have lost the Hubble Space Telescope. So the designers said, hey, we can fix that. Let's machine the middle of the bolt off so it's really thin. And that way, if the bolt gets stuck, it'll break in the middle of the shaft, not at the other end. And we'll put a feature such that if the bolt breaks, the old camera will stay in the telescope forever, but at least it will hold in place so that you don't have a big gaping hole. The difference between the torque that we were going to apply, which was something over 48 foot-pounds, and the braking torque, 58 foot-pounds, is very hard to feel. And so what Drew reported is it turned. And at this point, we don't know whether we broke it or we broke it loose. Now, we have lots of help. So here's a view that we took with a handheld camera looking towards the cabin. So this is Megan looking through the window. There's the EVA person here. You can't see it because of the reflections. Here's the overhead windows. The nose is that way. She's looking a little worried at this point. And inside was Mike Massimino. And remember I told you we have instructions for everything? Well, the instructions for what happens when things go right is really thin. The instructions for what happens when things goes wrong is really thick. So we have the what happens when things go wrong. So it's not just Drew and I out there turning wrenches and tightening bolts and stuff. We have the other 5 crew members inside as resources. And so he's reading a procedure that says, you know, loosen the bolt with this torque, with this tool, so many turns. If it doesn't turn, go to the what goes wrong book, opens that up, and it says, you know, the first step is turn the wrench up to a higher torque. Okay? Now, we actually have torque limiters, things that slip if you get to too high a torque. So it says first try it at a higher torque. Then it says go get another tool with a higher torque. And then it says panic. No, it says then take all torque protection off and turn it, and hopefully you get it. But it also says call the ground first. You know, because it's not just the 7 of us on orbit. We have hundreds of engineers and scientists and technicians and thousands of space shuttle folks on the ground watching over us. So I told you I'm a Car Talk fan. So you're listening to Car Talk with Click and Clack, the Tappet brothers. Go ahead, Florida caller. So here's some NASA guy with a mustache. A lot of us have mustache. And it says, okay, here's my problem. I actually did call Car Talk from space on my second mission. Again, another story. But anyway, the ground said, hey, we don't have any ideas. Go ahead and crank on it, and hopefully it'll work.
3. Woohoo, it's moving out. 4. Great job, great news.
It was tougher to do than we thought, but you know, it has ended with just beautifully. Well, I've just lost 5 years of my life.
That's David Leckrone, the Hubble project scientist. You know, and the people on the ground, it's much harder being on the ground because on orbit, you know, you feel like you're in control of some things. On the ground, they're watching us and, you know, really don't have the ability to affect things. But there's a big team of folks. This is Frank Ceppolina. He's the head of the whole servicing activity. Dave Leckrone. And these are engineers and scientists that helped us build the tools and such. So we were able to get that camera out. That allowed us the next day to change out those gyroscopes. They're in this little box here. Here, Mike Massimino and Mike Good inside doing the gyro repair. We replaced the batteries. You know, they're not AA batteries. They're actually 400-pound nickel hydrogen pressurized gas batteries. Here's one of those power tools with a wrench on it and a socket and an extension that we use. That allowed us on the next day to change out that CoStar instrument. Remember, CoStar are the contact lenses. We don't need that anymore because all the new instruments have the correct prescription integrated into their optics. So we're taking out the CoStar. Now, I mentioned that the suits are really hard to work in. And so I convinced Drew, my spacewalking partner, to go to the gym every single day and lift weights because I said, this CoStar weighs 800 pounds. You're going to have to be able to handle it in space. And of course, it's floating. But more seriously, we did go to the gym just about every day, lifting weights, because it's just hard to work in the spacesuit. It's very stiff. And literally, from a physics perspective, how many physicists or physics majors or people who took physics in high school are there out there? Okay, so work is the integral of force times distance, FDX. And every time you move, whether you're closing your hand, moving your arm, you have to fight the spacesuit. And just moving your arm from here to here is like taking a 25-pound dumbbell and lifting it. And you do that over and over all day long. And you know, it's hard on the joints and everything else. And so we did have to work out a lot. But we took out that old instrument and put in the new instrument, which is the Cosmic Origin Spectrograph, super-duper spectrograph in the ultraviolet. And so here's what it looks like from the helmet cam that's on top of our head. We didn't have these cool GoPro cameras back then, so it's regular resolution. But these are opening the doors on Hubble. Hubble was designed to be serviced, so it actually has doors on it. So that's CoStar coming out. You may have seen Drew do a quick thumbs up. That's because every time we did it in the water tank practicing, which we did about 12 times for every 12 hours for every 1 hour on orbit, the thing got stuck. So when it came out for real on the real day, he was pretty happy. We put in the new COSTAR instrument, cosmograph spectrograph, and then we tried something that's never been done before on orbit. I'm inside the telescope doing surgery on the advanced camera for surveys. It had died a couple of years earlier. It had no power. I had to cut through an aluminum panel, take off some tiny screws. These are little number 4 screws. You'll see them in a minute floating around. How do you take screws out in space? With a screwdriver. If you look carefully on this piece of plexiglass, you can see little screws floating around, because we couldn't lose a single one in the telescope. And then I had to pull out electronics cards, 4 electronics cards. And the edge of those, of course, is like any electronic cards, razor sharp. I'm wearing a cloth suit. My life depends on it, so you got to be careful. You can't touch it. That's why we had that weird tool. So I was able to remove all those 4 circuit cards, put 4 new circuit cards in, cut through the aluminum, put new electronic cables on, and bring the advanced camera for surveys back to life. And here we are cleaning up the payload bay at the end of the day. There's the Baja Peninsula, Mexico, a few clouds, 5 miles a second over the Earth. We had trained for this. This is regarded as brain surgery in space, the hardest thing humans have ever done in space. And I was incredibly happy coming in at the end of that day. And it worked. Everything worked terribly. Virtually everything that could go wrong did go wrong. But because we had trained so much and practiced so much on mock-ups, everything that happened on orbit that went wrong, I had seen before on the ground in practice. So it seemed normal to me that all those things were going wrong. I was really happy. That night, I slept better than I think I've ever slept. I sleep the best in space. Slept through the night. And we typically wear eye shades and earplugs because it's noisy, and have 16 sunrises and sunsets a day, so it gets light and dark and light and dark. And in the morning, we have an alarm that goes off. It's a tone. It goes boop. Not very loud, but it goes off. And then we start getting up, and then a few minutes later, about 15 minutes later, the ground will play up wake-up music. You've probably heard of that, usually tailored to an individual crew member. So the tone went off. People started moving around, going to the toilet, which sounds like a jet engine starting up, playing the music. I hadn't stirred a bit. I was still in my sleeping bag, and Megan went to get Scooter. It's not very big volume, so he was upstairs sleeping and had woken up, and she went and got him and brought him downstairs, and she said, "I think John's dead." So he grabs my foot and shakes me, and I go, "Good morning." But it was great. But years of stress, released after that spacewalk. Sometimes I find, though, that modern culture is way ahead of the real space program, and certainly Arthur C. Clarke and his amazing genius in predicting communication satellites, and you name it. He had thought of it and written about it either in nonfiction or in fiction. And so the idea of an astronaut in space taking out tiny screws to repair a scientific instrument was not new to Hubble. We invented dozens of tools, worked hard. It gave me an excuse to go to the hardware store and buy lots of new tools from my garage that I then tested out in the water tank at Johnson on Hubble, which is always a nice thing to do. But in fact, popular culture had already anticipated
It's
this.
a lovely day for a launch here live at Cape Canaveral at the lower end of the Florida Peninsula. And the purpose of today's mission is truly, really electrifying.
That's correct, Tom. The lion's share of this flight will be devoted to the study of the effects of weightlessness on tiny screws.
Unbelievable. And just imagine the logistics of weightlessness. And of course, this could have literally millions of applications here on Earth. And everything from watchmaking to watch repair.
So I had to remove dozens of these tiny screws, cut through the aluminum. But that was kind of the warm-up day, because on the next day, Mike Massimino and Mike Good had to go out and remove 117 tiny screws on the Space Telescope Imaging Spectrograph, another one of Hubble's crucial instruments, the next day. And the STIS instrument, Space Telescope Imaging Spectrograph STIS, had failed earlier, and we had been training and developing tools to repair this when the advanced camera failed. And we applied some of these techniques to that. It just happened the day before. But before Mike Massimino could start working on the tiny screws, he had to remove a handrail like this that was covering the panel he was going to remove. And the handrail was held on by some big bolts, the kinds of things that you can't screw up. Unfortunately, working in a big bulky spacesuit, you can screw up anything. And unfortunately, he stripped one of those bolts. Now, it's not that surprising. The bolts are stainless steel, 308 stainless steel, I think, for those of you who are somewhat technical. And the bit was tool steel. And when he went to put the tool in, the bit was spinning, and it's a socket head, and it just rounded out the inside of the socket head. And we were screwed. For 4 hours, we tried to get that handrail off, and it wasn't going to come off. Mike had to recharge his oxygen. We looked at all the tools we had outside, and there was nothing that was going to help. Inside, we actually had a 3/8 socket that would have allowed us to remove the base of the handle and get it off. But that would have involved the astronauts coming in, repressing the airlock, and going back out. And we'd already eaten up 4 hours, and we thought, we don't have enough time in the day. Fortunately, the ground came to the rescue, and I'll just play and show you what happened.
Okay, Drew, I'm having trouble with this one on the lower right. I don't want to strip the thing.
That darn handrail.
It was way stripped.
Houston, you ready for this?
Yeah, we're ready.
Okay, Mass, you have a go. Here we go. So, disposal bag, please.
So the ground called up and said, John, do you think mass can pull 60 pounds of force? I said, at this point, I'm sure he can. And so we asked him, and he said, of course I can. And you see the result, positive result. Now, that handrail is covering up the panel that he then had to remove all the other screws. After the flight, I said, how did you know about 60 pounds? Was that a guess? Was that a calculation? And they said, oh, no, we built a test.
Go ahead.
So while the spacewalk was going on, they built this. They took a fish scale, and they measured the force. And even better, they didn't show that video to anyone. Because you can be sure the safety guys would have said, no, we're not going to let him do that. He'll get killed. He'll shoot his eye out. For those of you who are a Christmas Story fan. So fortunately, we were able to repair this disc. That allowed us on the final spacewalking day to put in a new fine guidance sensor. That's me on the end of the robotic arm. Now Drew is the free floater. This is Hubble in the payload bay. There's the back of the orbiter, solar arrays. The fine guidance sensor is really what allows us to lock onto stars and stay there for hours and hours and hours. We finished everything off. We actually put some new insulation on the telescope. Here's Drew doing a handstand. Earth in the background. Just an incredible, incredible mission. We did everything we had anticipated and a little bit more. That allowed us on let's see, this would be the 8th day of the mission to put Hubble back on the end of the robotic arm. Megan put it on the end of the robotic arm, lifted it up. Everything is ready to go. We deployed it. So here it is floating off into the distance. Here's the Earth. It looks like we're over Australia. Kept getting smaller and smaller, and at one point we went into darkness, into the Earth's shadow. Hubble went into the Earth's shadow. And that's the last time human eyeballs have put, as far as we know, put their eye, well, I guess gravity. No, anyway. Human eyeballs have seen the Hubble Space Telescope, but it's continuing to do great. But for us, our main job was over. Well, for the mission specialists that were doing the spacewalks, we had to put everything away. Scott Altman still had to do the little job of landing the space shuttle. But we had a couple of days just to relax, have a meal together. I like to hang from the ceiling like a bat. All of our food's in little pouches. But we also have tortillas and chicken in pouches and stuff like that. So this is Drew making a chicken tortilla. You can see his spoon there, the tortilla floating. Surface tension causes the chicken to stick to the tortilla, and we're off to the races. Now my son, who at the time was about 7 years old, said, Dad, can you make a ball of water, float it in the middle of the space shuttle and take a picture of it? So I did. So here's a ball of water. That's Drew Feustel. And I realized that a ball of water is a lens, a convex lens, and I focused the Nikon SLR on the image in the lens rather than on Drew to show my son that it inverts the image just like a convex lens. And how cool is that? Drew does not have a nose that big, that, you know, it's, as you saw earlier, so it was kind of cool. And then I said, Drew, get really, really close, and let's see if this thing's a magnifying glass. So, you know, it's actually still floating in front of him. We're looking into his eyeball. It's kind of cool. And, but then as soon as it touches his face, then surface tension wins, and it just spreads right out. It's a fun thing to do. The most fun thing to do other than spacewalks is to look out at the Earth. I just love looking at the Earth. These are the Cape Verde Islands off the coast of Africa. And as the winds, the trade winds, go over these islands, they cause vortices, wake vortices, Kármán vortices in the trail. And you can see those go on for hundreds of miles. It's just very cool to see all the different phenomena in the Earth. Of course, sunrises and sunsets are really beautiful. I know this is actually a sunrise. One, because I took the picture, and two, because it's so bright you can't look out. And you know, even with sunglasses, you still have to squint a little bit. And so the trick is, you wait until you see the glow on the horizon. You set up the camera, and you just start shooting and count to 5 and shoot again. And eventually, you don't have to look out. The sun comes up, and you get beautiful pictures like this. Really pretty amazing. Now, we had a situation where we took off from Florida. We like to land in Florida. But the weather was really bad. And we looked out the window and we saw huge thunderstorms, and the ground said, you know, you're not going into Florida. You got another day, and then they gave us another day. So we had a chance just to play on orbit. So I call this feeding the fish. Those are peanut M&Ms. Not only did we do water, that's orange juice. Well, it's actually Tang, if you want to know the technical name for it. Here's water. But we also did serious physics experiments. Here's a study of the rotation of solid objects around various axes and conservation of angular momentum. You can see one of the sleeping bags in the back. Now, while we were down doing physics, the crew on the flight deck was actually playing video games. Here's the Land the Space Shuttle video game. And actually, this is a different time. I was filming this. That's the runway. Once Scooter lands, Scott Altman lands, it gives all the data on how hard he hit and things like that. And each time I filmed it, I said, oh, I've had the camera set wrong. Can you do it again? Because I wanted him to practice a lot. He hadn't flown in a couple of weeks. And we were waved off. And finally, we got the call that we weren't going to go to Florida. We're going to go to California. So Scott put his shades on, a little California music. Megan said, get to work. So here we are getting back in our launch and entry suits. We're now actually entering the Earth's atmosphere. The nose of the shuttle is about 4,000 degrees, about 2,500 degrees outside rest. You know, that's the plasma. Basically, we're a meteorite entering the Earth's atmosphere. You know, finally, about 500 miles off the coast of California, we spotted the runway. Here we are, just a few miles away. We're going through 12,000 feet, doing over 300 miles an hour, 21 degrees down. And for 5,000 miles, we've been a glider. We have no engines. We have one shot. And we have to land on a runway that's 200 feet wide by 15,000 feet long. At about 300 feet, we put the landing gear down. And Scott Altman guided us to a beautiful landing, middle of the runway. We put out a parachute. That's actually not to slow us down. That's so when the nose hits the runway, it doesn't hit quite as hard. Once the nose is down, we get rid of that parachute. And we roll to a stop. At the time, we thought it was the last flight of Atlantis. Since then, we added another mission. But we rolled to a stop on the runway after traveling about 5 million miles, 197 orbits of the Earth, doing 5 spacewalks, grabbing Hubble, deploying Hubble, doing everything that we needed to do. However, the big question is, you know, we didn't break the Hubble as far as we knew, but even at landing, we didn't know whether Hubble actually works anymore. That takes a little bit longer, and when the first images came out, you know, we were very happy. I think you all know the Hubble is doing great. So I thought I would show you a little bit of what Hubble has done with it, but the first thing is a quick tutorial. So Hubble only takes black and white pictures. Everything else is a fake. What, no reaction at all? Boy. No, Hubble really does only take black and white pictures. But it takes it through colored filters. When you shoot with your digital camera, say an iPhone, it actually takes 3 pictures simultaneously. The image sensor in the phone has a piece of silicon, and when we think about it, let's say it has a 3 megapixel sensor. It actually has 9 megapixels because it has a set of green pixels, green, red, and blue pixels. And it takes all 3 simultaneously, and then the little computer inside combines them into an image. Well, Hubble only has 1 sensor per camera, typically, and it takes through 1 color filter and then another. So if we want to look at a galaxy, this is how it would look. And it's very sharp, you can see stars, but as far as cool factor, it's not much better than Hubble's. But what it does is it takes it through a red filter, say, a green filter, a blue filter, and each of these filters mounted permanently in Hubble has been chosen to correspond to a different type of physics so that we can learn about what's going on. Sometimes even a 4th filter. This particular one is just hydrogen light, not oxygen light or nitrogen or other things, sulfur. So we take those 4 images and then we combine them into 1 image. And that's what makes our beautiful images. So that's how Hubble does its beautiful imagery. And beautiful it is. This is a galaxy with about 100 billion stars, kind of like our Milky Way. But there are things that are much more beautiful. And I think that's one of the reasons why Hubble is such a popular telescope. It's not just that it does great science, but that it's shown us how beautiful the universe really is. It's not just points of light. This is a nebula of gas and dust. It's taken in the light of oxygen, nitrogen, and sulfur. And that's glowing in those characteristic colors of those elements like a fluorescent light does. Inside the middle of this gas and dust, and there's a lot of silicates, sand and other things, very, very small particles. And they're collapsing, and inside of this dust cloud, and we can't see it, a new star and a new solar system has just been born. Hubble can't see that because the light doesn't get out of this dense cloud of gas and dust. Now inside, once the star turns on, its own light starts an expanding bubble pushing out the gas and dust. And from the outside, all of its neighboring baby stars are evaporating this nebula so that after a few 100 million years, all of this will be gone and we'll be able to see the new star. I don't know about you, but I'm not going to wait 100 million years to see that star. I won't make it that long. But fortunately, physics comes to the rescue, because even though visible light, the kind our eyes see, can't get out, infrared light has just the right wavelength to sneak between all those dust grains, and we can see inside. So there's the baby star. We kind of knew it was there because we saw jets of material coming out. You can see sort of the wispy, ghostly outline of the nebula. And I'll go back and forth a couple of times because it's fun. And so this is the power of those extra colors that I mentioned up front, that Hubble can see infrared light that we can't see and ultraviolet light that we can't see. We can reveal details of the universe that are otherwise unseen to learn about what's going on. And so this particular star, T Tauri star, it's just a name astronomers have given stars of this type, is born, and it's one of the characteristics is it has these jets. And so we know that orthogonal, perpendicular to those jets, is a disk of gas and dust that's spinning around and that planets are forming. And one of the things Hubble has taught us is that planets form about the same time stars do. It's not a much later phenomenon. They form at about the same time. Now that's how stars are born. Dust collapse, stars turn on. When stars get really old, like me, they get really angry and they blow up and yell at people. No. This is a star about 5 times more massive than our sun. It's running out of fuel in its core. It's starting to burn heavier elements. And as a result, it gets disrupted and it blows off its outer envelope, but it continues to shine. And so all of this gas and dust and light that we see, the emission from that, is the result of a series of episodes of this star blowing off its envelope in its death throes. And eventually, it'll just get rid of so much gas that it turns into a star called a white dwarf. This may be the fate of our sun at some point 5 billion years from now. And we can see that there were various episodes, because here's one front, here's another. Those two probably go together. Here's the more current one. And these are episodes that then get lit up by the light from the star and glow, again, like fluorescent lights. So this is the end point of stars. So Hubble has taught us about the distant universe, black holes, star birth, star death, and other things, and lots of other surprises. After that first servicing mission, one of those surprises is that we discovered that a comet, Shoemaker-Levy, after the famous planetary geologist Gene Shoemaker and Gene Levy, Shoemaker-Levy 9 had broken up into pieces as it was about to hit Jupiter. Fortunately, in 1993, we fixed Hubble. In 1994, these impacts hit Jupiter, and wow, we saw these huge scars on Jupiter. Now, Jupiter is massive. We weren't sure whether it would just be absorbed into the atmosphere and disappear, but these things lasted for a long time. And astronomers were so thrilled that we had fixed the Hubble in time to see this, because this is a once-in-a-lifetime, estimated once-in-a-1,000-year event, and we were just lucky enough to see it. We were so special. Well, in 2009, we fixed the Hubble Space Telescope, and shortly thereafter, May, we fixed it. By July, we saw another scar. This one was actually picked up by an amateur astronomer in Australia, and he thought there was something wrong with his camera, so he took another image, and it was still there. He called a friend of his in the Philippines and said, "Hey, is Jupiter still up?" He said, "Yeah." He said, "Will you take a picture of it for me?" I said, "Okay." He said, "What do you see?" And he said, I see Jupiter." And he said, "Look at the bottom and tell me if you see a black spot." And he did too. And then he knew it wasn't his telescope. He, alerted the folks at the Space Telescope Science Institute. They took an image and they saw that Jupiter had been hit again by another asteroid. And so now we know that it's not a 1-in-1,000-year event, once-in-a-lifetime event. Every time we service Hubble, Jupiter gets hit. Now, just to set the stage, this is interesting. Now it's a common event. In fact, we see Jupiter getting hit all the time now. We just weren't looking. Nobody realized what a dust magnet Jupiter is for the solar system and how lucky we are that we have a Jupiter. Here's the Earth to scale. And so if that same object had hit the Earth, I would have had to cancel tonight's lecture. Now, I'm going long enough, you probably would be thankful that, no, just kidding. But this is one of those things where, hey, you don't see something like that every day. But in fact, we do. We see it all the time. The universe, the galaxy, our solar system is filled with a lot of debris. And we know that because we can look at the moon. Tycho is the youngest big crater on the surface of the moon, and it's easy to see with your naked eye, and you see the rays going out. It was hit, I don't remember exactly when, but it's some tens of millions of years ago. It's a canonical complex crater. The moon got hit. There was rebound of material, so the central peak is actually from the inside of the moon. As this all got melted and it rebounded, and we can see that, Tycho's near the bottom here, we can see that because the elemental abundance is different than the rest of the crust. We've been able to map this in great detail with the Lunar Reconnaissance Orbiter. We've even used Hubble to observe the moon. This is with that advanced camera for survey. This is Aristarchus, another very young crater, just some tens of millions of years old. And the reason it's so bright in the ultraviolet is because this material has recently been excavated and it hasn't been weathered by the solar radiation, the ultraviolet, and micrometeorite hits over time. So we're able to learn a lot about that. So I'm sure all of you saw the Chelyabinsk imagery of a large meteor coming into the atmosphere, and it broke windows and scared a lot of people. It didn't kill anybody, but we're getting hit all the time. Things like Chelyabinsk are actually common. Fortunately, ourselves and many people around the world, part of my NASA science mission is actually to look for potentially hazardous asteroids and categorize them and characterize them. For really large objects that are like planet enders, we have a really good catalog of most of the stuff that's out there, so I wouldn't worry about anything tonight. Getting to smaller objects that could be city killers, we're not doing so well, but we're working on plans to survey that. But at some point, I hope we prove, 1, we're smarter than the dinosaurs, and 2, smarter than this alien, and that we will survive. And we're working on mitigation of if we find something long enough in advance, we could actually give it a little bit of a shove so it would miss the Earth. So we're studying all of that at NASA. These are some more recent images with the new wide field camera in the infrared. This is what we could do in 2001. This is now with this new infrared capability. We can see much more detail inside of these star-forming regions where baby stars are born. Some classics. This is the Horsehead Nebula. If any of you have ever tried to see this in a small telescope from DC, it's a big challenge. But we now have enough information that we can synthesize a 3D view, the Starship Enterprise view, flying through one of these clouds where baby stars are being born, baby planetary systems. Really engaging, and it gives you much more of a feel of what these are like. They're no longer two-dimensional objects of art. They become living objects the way they really are in space. We've come quite a long way since Galileo. Here's another one of those fashionable hats. Mike Massimino. Here I am trying to image the Galilean moons. We've really been able to span the entire universe. With these new cameras, we have now observed one of the earliest galaxies ever. And when you look at, and this is another 3D view, a lot of these galaxies are spiral galaxies like our own. But every single spot in this image, this is a real Hubble image turned into 3D, every single spot is a galaxy with tens, hundreds of billions of stars. We now know there are 200 billion galaxies in the universe, each of which has about 100 billion stars. And some of these objects are so distant, the light has been stretched out into the red that we can't see anymore after that. So we're working on another telescope that goes beyond that. Let me just show you another couple of iconic images. The Pillars of Creation, the Eagle Nebula with the old camera. Here's the new view. We're celebrating Hubble's 25th year on orbit. And as I give talks to student audiences, I'm amazed to think that everyone in the audience, except for some of the teachers, has been on this Earth with a Hubble Space Telescope. They are the Hubble generation. And that's amazing to me, that they get to know these images, basically from birth. So Hubble is really pretty incredible, but what's next? No chimpanzees in this one. The James Webb Space Telescope, coming to a sky near you, October 2018. This is the James Webb Space Telescope. This is our next generation telescope after Hubble. It's no offense, but enough with the French horns. Where's our French horn player? There she is. I love the French horn. So that's the James Webb Space Telescope. Instead of a telescope with a tube, this is an external telescope. It's segmented instead of one piece of glass. We did that because instead of being 2.5 meters across, it's 6.5 meters across. It's gold-coated because it sees that infrared light, that very spot of light in the red, that's that distant galaxy. We want to see what it is. We want to try and understand these baby galaxies and see further back to see the first stars, the first galaxies. To do that, we need to collect more light. You see this weird shade here. The light from below is indicating where the sun is. All of this will be shaded and will cool down to 40 Kelvin. 0 Kelvin is absolute zero. So this is going to be a really cold telescope, 400 degrees below 0 Fahrenheit. And all of this will get cold because things that glow in infrared are cold. So we don't want the telescope to be really bright. If any of you have seen one of these cameras that shows heat, if the telescope is hot, all we're going to see is light from the telescope, so it's really cold. So this is an incredibly challenging project. We've been working on it for a number of years, and it's going to be able to see the very beginning of galaxies, the first stars, everything in between that I showed you in that story. But of special importance is it's going to be able to look at those nearby planets that we're discovering and try and understand whether it has water on the surface, what are some of the elemental characteristics, the beginnings of this story of trying to find out if we're alone in the universe. We'd have to be really lucky for James Webb to do it. We need, I think, a bigger telescope to do that. but it certainly will go where no Hubble has gone before. So from Galileo to telescopes on the space shuttle, 20 years ago I was on my first mission, right about now, and we flew the Astro 2 observatory in the payload bay, and I was a telescope operator and a scientist on orbit. Then the Hubble Space Telescope. With the advent of rockets like the Space Launch System, we can launch much bigger telescopes, and I think someday, following on the Hubble, assemble a much larger telescope that'll be the one that will be able to tell us by looking at planets that are around nearby stars whether we're alone in the universe, whether we see signs of life, because when we look at the Earth's atmosphere, it's obvious to an astronomer there's life on Earth. It has all the signs. We broadcast to space our plant life, our pollution, the geologic signs that there's life on Earth are broadcast out to space. We would be able to look at another planet, hopefully, and determine that. So with that, I've pretty much come to the end of my story, the Hubble Space Telescope, but it's certainly not the end of the Hubble Space Telescope story. In fact, I believe we've only gotten one Nobel Prize so far from Hubble. The story of Hubble is just beginning. If you want to learn more, spacetelescope.org, hubblesite.org, nasa.gov. If you have way too much free time, you can follow me at SciAstro on Twitter. And this is the Hubble 25th anniversary. There's going to be a lot of events here in town, specials on television, and around the country. So I hope everybody helps to celebrate Hubble's 25th anniversary. Thank you very much.
Thank you, John. We have time for some questions. We have a procedure for questions. There are microphones. The people with the microphones will hold them up, and the people with questions will be kind enough to hold their hands up long enough for the people with the microphones to see them. Let's start over there and over here. Let's start on the right first. If you'll stand up, tell us your name, tell us whether you're a member. If you're not, it's okay, no penalty. You can still ask your question. And ask your question.
Okay, my name's Elisa Wynn. I'm here with a member. My question is kind of specific and not galaxy spanning. But when you're in actual orbit, we see all of these visuals, and it's very difficult to know what's been naked eye sort of visualization as opposed to enhanced. When you're coming up on something like Hubble or ISS, excuse me, my voice. At about what distance are you actually visualizing it, and it doesn't look like a star anymore? And tens of miles or hundreds of miles? How far can you see?
Tens of miles. It starts to start getting bigger. Prior to that, so at a few thousand miles, it's on over the limb of the Earth, so you don't see it. So eventually, you start seeing something that you have to distinguish: is it a star? Is it another satellite? Is it the target? Eventually, it gets close enough that it's always there in the same point in the window, and you know that you're coming up on your target. Plus, we have computers that tell us exactly where to look. Once we start getting about 10 miles away or so, that's when the binoculars come out. And you start trying to see, okay, can you see solar rays, and this kind of thing. And it's really a human element. It's this, very akin to, land ho, or in, telescope case, whoosh, trying to see, okay, there's the hint of land. Now, what land is it? What does it look like? And that's the space equivalent. Once you get to about a mile away, then it's easy to see, that it's a telescope, and everybody starts getting really excited. And now we're looking for, hey, for me anyway, how did it fare between the last time I was there? Is it still in good shape and that kind of thing? Yeah.
We have another question over here.
Hi, I'm Michael. It's my very first time here, not a member yet. Last year, I think there was a news article about maybe 2 or 3 Hubble-class telescopes that hadn't been finished. I think they came from NRO or something. Are those ever going to fly, and are we ever going to see a visual light-range telescope like Hubble again, or is this it?
So we did, in fact, get 2 telescopes from the National Reconnaissance Office that were not either, I know they were never flown. I don't know whether they're part of a program that flew or not, but they're two 2.4-meter telescopes. Very different than Hubble, though. Hubble, I should have said that, the Hubble Deep Field, the image that has thousands of galaxies in it, is essentially equivalent to holding a soda straw up at arm's length and looking through it. And in that tiny little view is where we see in the extreme deep field 11,000 galaxies. That's how narrow Hubble's view is. The NRO telescopes, if we convert them to a space telescope for astronomy, will have a much wider view. So imagine that you're sending out, not to pick on the attorneys again, a legal brief. So you have an 11 by 17 envelope. Okay, and you put your papers in that 11 by 17 envelope, and you peel off a little stamp and you stick it in the corner. The Hubble Deep Field image is that little stamp. When we use these new telescopes, they'll have galaxies across the whole envelope. So it's really going to open up our view considerably to be able to do cosmology. We're going to try and use those telescopes to meet the scientific objectives that were laid out in the scientific consensus called a Decadal Survey from Astrophysics for something called WFIRST, Wide Field Infrared Space Telescope, or Survey Telescope. And it was designed to study, the history of the universe, cosmology, to try and analyze something, dark matter, and something mysterious called dark energy, which is the acceleration of the universe. The universe expanded for the first 6 billion years and was slowing down because everything was pulling on each other, all the galaxies, all the mass, and it was slowing down because of mutual gravity. And the big question a few years ago, 1997 timeframe, is what's the fate of the universe? We don't want to know just where we're coming from, we want to know where we're going. And there were several options depending upon how much mass there is in the whole universe. One option is it would continue to slow down, stop, and then recollapse in a big crunch. I kind of liked that idea. You'd have a big bang, a big crunch, a big bang, a big crunch, and every 50 billion years you get a new universe. Another option is it would just expand, slowing down forever, and just continue to slow down, but there wasn't enough matter in the universe ever to cause it to stop. And eventually, things would get farther away, but it would be so long before, things were so far away that, you don't worry about it. Well, in fact, that's not the way the universe is at all. In the last 6 billion years, so the first 6 billion years was slowing down, and for some reason, in the last 6 billion years, it's been speeding up. And there's no physics that can account for that. This was the reason why Brian Schmidt, Saul Perlmutter, and Adam Rees got the Nobel Prize using Hubble, was the discovery of this cosmic acceleration. Now, things don't accelerate for no reason. There has to be some force, some pressure. And any pressure or force has associated with it an energy field, an energy. And so we don't see what it is. Just like dark matter, we don't see what dark matter is. That's why it's called dark matter. So it's called dark energy. Nobody said astronomers and physicists were particularly clever. Just look at the names of quarks. So this dark energy, WFIRST is going to help us try and understand more about that dark energy by surveying much larger volumes of the universe, looking for these distant supernovae, and also study exoplanets in much greater detail. So we're actually trying, that's one of my main jobs right now is trying to get that telescope started. So I hope sometime about 10 years from now that will be doing amazing science on orbit. As far as the follow-on to Hubble, though, we have lots of great ideas, but that's a few years off still. But I think we will have another Hubble.
Carl, and then one more.
Hi, Carl Merrill, a member of the Society. 3 quick questions. One is, how do you change the filters since you only have the one sensor? Number 2, you have to constantly maneuver the Hubble, so how much fuel do you have for that? And the third one is, can we service the Webb telescope?
You charge extra for 3 questions.
Okay, so I'll answer the last one first. We cannot service the James Webb Space Telescope, partly by design and partly because it's going 1 million miles away from Earth, away from the sun. And it's going away from the Earth because the Earth is hot. We need to get somewhere cold. So it's going to a point that's called Earth-Sun L2. It's the second Lagrangian point It's a mathematical point in space. It actually doesn't exist. It's just space. But the pull of the Earth and the Sun allow you to have a relatively stable orbit there. And so it'll point away from the Earth, away from the Sun with that sun shield, get very cold. But it's too far away. We don't have a way to get there. And it's so delicate, we have to fold it up like origami and transformer combined to fit in the rocket and then deploy once we are on our way. So we haven't made any way to service it. Now, that doesn't mean it can't be serviced. It means we didn't plan for it. So it has enough fuel for a lifetime of 5 years, almost for certain. And then if we manage it really well, 11 years. And after that, that's it. And that's acceptable. I'd like to see it twice as long or 3 times as long. But out there in deep space, its detectors are actually going to degrade to the point that without the ability to change out the instruments, it probably won't be worthwhile much longer after that. Hubble has no, second question, Hubble has no fuel whatsoever. So it is slowly spiraling in from just a tiny bit of atmospheric drag at 350 miles. At its current rate of spiraling in, it's going to enter the Earth. It's going to actually be uncontrollable sometime around 2037. And then some 3 or 4 years after that will start to tumble, and then we don't know where it'll go, but it's going to enter the Earth's atmosphere, and most of it will burn up. Instead of using propulsion from rockets to maneuver from place to place, because it's in Earth orbit, it uses gyroscopes. It has 4 gyroscopes. They're spinning very fast. And by slightly changing the torque on one of them, we can change the attitude of the observatory. Now that's fine until all the wheels are spinning at their maximum speed, and you have to desaturate them. You have to get rid of angular momentum somehow. You saw me doing that in the payload bay. And it has some large magnets, electromagnets. And we turn on the electromagnets, and we slow down those wheels, torquing against the Earth's magnetic field, called magnetic torquer bars. Very, very clever. Now, the best way is just manage the torque of the 4 gyros so they don't get to saturation very often. So that's how it points from place to place. Now, the good news about the Hubble is it likes to stare in one place for a long period of time. But we do lots and lots of observations every day. And your first question is on filter wheels. And the answer is each of the scientific instruments has its own set of filter wheels. So when we replace the new instruments, we get a new set of filters as well. So each of the instruments has a set of filters. And in the wide field camera, there's actually 2 separate cameras. The wide field camera 3 is actually 2 cameras, and each camera has its own set of filter wheels. One's in the visible ultraviolet, and one's in the infrared.
Last question. Anybody want the last question? We have one right there in the back. No, behind you.
Hi, my name's Isaac Schomer. I am a member. And my question is, recently there's been some research out of Purdue University showing that radioactive decay of some elements is affected by the distance to the sun. So I'm wondering if NASA has any plans to take up some radioactive material into space and measure its decay rate in terms of how far or close it is to the sun.
Okay, so I'm not familiar with that research, but I can tell you that radioactive decay is a natural clock. And there are several reasons why radioactive decay can be affected by distance from the sun. One of which is, depending upon the mechanism, is cosmic ray flux and neutrinos. But a fundamental reason is that general relativity tells us that clocks run differently depending upon the local gravitational field because you're accelerating. Right now, we're all accelerating at an ignominious 1g. 1 times the force of gravity on the surface of the Earth. When we're in orbit, we're further away from the Earth, so that's a smaller gravitational force. So it turns out actually that our clocks run slightly faster. However, we're traveling 17,500 miles an hour. And general relativity also tells us, through special relativity, that the faster you go, the slower your clock runs. So in fact, I'm actually a few microseconds younger than I would have been if I'd never gone to space. And so we use those effects of relativity to measure the speed of clocks. And we've taken radioactive material to space, but there's an easier way to do it, and it's through atomic clocks. And so atomic clocks use a particular vibration, a particular frequency of light from an atom, say a cesium atom. cesium atomic clock, to measure time. We don't actually have a standard meter bar anymore either. We measure distance by numbers of wavelengths of light. But we use these atomic clocks as extremely precise clocks. There are other extremely precise clocks in the universe. Neutron stars. The mass of our sun, the size of suburban Baltimore, spinning sometimes hundreds of times a second. And it's so stable, that angular momentum, and it's blinking at us in radio waves, so we can use that as a clock. But we can carry local atomic clocks with us. And when we move those clocks from the surface of the Earth to some orbit of Earth, we actually can have two clocks that start synchronized, launch one, put it in orbit, and we can measure the shift in the time that verifies general relativity and special relativity. So we know those clocks are running at different rates. That's how GPS works. GPS isn't distance measuring in the classical sense. We're measuring time on all these different satellites. And by the difference in time corrected for these effects of general relativity and the fact that clocks run in different speeds, and the amount of time it takes for the signals, we can figure out where we are on the Earth to great precision. So really, GPS is flying atomic clocks in space and measuring the fundamental laws of physics very accurately. Well, thank you all very much for your attention and for staying this late.
Thanks all. Thanks all.
Okay.
Thank you, John, and appreciation for spending dinner with us and giving this wonderful lecture. We are giving you a small token of appreciation, a signed copy of the announcement of your talk, signed by the members of the General Committee on behalf of all of you, members of the audience and members of PSW.
Thank you very much. I appreciate it.
Thank you. Thanks.
Thank you again.